Hi, welcome to Chemical Bonding. My name is Dr. English. Today we're going to talk about molecular polarity with polar molecules. Specifically, we're going to look at the asymmetrical distribution of charge within a molecule, common shapes of polar molecules including linear shapes, bent shapes, pyramidal shapes, and finally tetrahedral shapes. Shapes that follow asymmetrical distribution of charge. So we're going to look specifically at polar molecules with polar covalent bonds. Molecules containing polar covalent bonds with asymmetrical charge distributions is what we're looking for specifically. The shapes that are found in these types of molecules include linear, bent, pyramidal, and tetrahedron, or you might hear the term tetrahedral. The first one that we're going to look at is a linear example. So we're going to look at the molecule HF. So what I'm going to do here is I'm going to start with fluorine, and we know fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And then we're going to put down our hydrogen, and we know that our hydrogen has 1 valence electron. And then we can see this shared pair of electrons right in here. So if we were to do a structural diagram of this, it would be H, a line to represent that shared pair, the fluorine, 3 pairs of non-bonding electrons. We know the hydrogen is 2.2 electronegativity, the fluorine is 4.0, so therefore the hydrogen is going to have a slightly positive charge and the fluorine is going to have a slightly negative charge. This means when we draw our polarity arrow, it's going to go from the hydrogen to the fluorine. Therefore, there is one arrow and one arrow only, which means it's definitely an asymmetrical distribution of charge. So you have a polar bond and a polar molecule. That's really what you're looking for. So you're going to recognize linear polar molecules because they're going to contain only one polarity arrow. One end of the bond is partially negative and one end is partially positive. The next example that we're going to look at is SH2. So we know sulfur has 6 valence electrons. So here's my sulfur, 1, 2, 3, 4, 5, 6. And hydrogen has 1 valence electron, so we'll put one right here, and we'll put one right here. And we have our shared pair of electrons right here and right here. And then if we draw out the structural diagram of this, we'll have sulfur with its 2 lone pairs, a shared pair with the hydrogen, another shared pair with the hydrogen, and we know for a fact that hydrogen is 2.2 and 2.2, and sulfur has an electronegativity of 2.6, which would make the sulfur slightly negative, the hydrogen slightly positive, another slightly positive, and when I draw my polarity arrows here, they're going to go from the lesser to the more electronegative. Same thing, lesser and more electronegative. The key thing to realize here is that those 2 lone pairs on sulfur have to be adjacent to each other. And if those 2 arrows are at an angle to each other, they're not canceling each other out. In other words, they're not straight across this way or straight across this way. If they're at an angle, the molecule as a whole is polar. So, specifically, include elements from group 16, such as oxygen, sulfur, selenium, and tellurium as our central atom. 6 valence electrons where the 2 lone pairs must be adjacent to one another. That's absolutely critical. Molecules that have a bent shape always form polar molecules. Now let's look at a pyramidal example, and for this we're going to use ammonia, which is NH3. So nitrogen has 5 valence electrons, 1, 2, 3, 4, 5, and hydrogen has 1. So here's my 1, and my 1, and my 1. And again, we can see our shared pairs here, shared pair here, here, and here. And if I was to do a structural diagram of this, it'd be the nitrogen, 1, 2, and then a single bond to the hydrogen, down this way, and it's all good. And then we'd go in and assign electronegativity values. Nitrogen is 3.0, hydrogen is 2.2, 2.2, 2.2, and we have our polarity arrows coming in, going from the hydrogen to the nitrogen, the hydrogen to the nitrogen, and the hydrogen to the nitrogen. And we know that the nitrogen is going to be slightly negative, and our hydrogens are going to be slightly positive, like we see right here. So in this case, we have 3 polarity arrows, 2 pointing inwards and 1 pointing sort of upwards. And in a 3-dimensional way, it looks like a little pyramid. Here on my screen, it looks like a T, where 2 arrows are canceling each other out this way, but then we have this other arrow pointing up. And really, when you have 3 polarity arrows, where they're all pointing towards each other and towards a more electronegative central atom, you're going to have a polar molecule. This situation will specifically include elements from group 15, including nitrogen, phosphorus, and arsenic as your central atom, contain 1 non-bonding electron pair on your central atom. In 2 dimensions, like drawing on a sheet of paper, this molecule is shaped like a T. The final example that we're going to look at is the tetrahedron or tetrahedral example, which is CH3Br. So we're going to start with a carbon in the center. So there's our carbon, 1, 2, 3, 4. We're going to bring in 3 hydrogens, 1, 2, 3 hydrogens. And then finally, to mix things up a little bit, we're going to bring in a bromine. So I'm going to put a bromine right here. And this looks definitely different from what we've seen before, where the bromine is our more electronegative element, and all of our electrons, when we draw out the structural diagram of this, are going to get pulled towards the bromine. So if we do the structural diagram of this, we're going to have a hydrogen, a carbon, a bromine, a hydrogen on top and beneath. Bromine will have its 3 lone pairs. The hydrogen will have an electronegativity of 2.2, 2.2, 2.2. The bromine has an electronegativity of 3.0. So if we were to put partial positive and partial negatives here, we know that the hydrogens would be slightly positive, slightly positive, slightly positive, and the bromine is going to be slightly negative. So when we do our polarity arrows here, it looks sort of interesting because all the electrons basically just get pulled towards the bromine, which means it most definitely has an asymmetrical distribution of charge. We're not seeing a mirror image here, and everything gets pulled to the more electronegative element. So this will specifically include elements from group 14, including carbon, silicon, germanium as our central atom. In 2 dimensions, like drawing on a sheet of paper, this molecule is shaped like a plus sign. This molecule is classified as polar, as bromine is the most electronegative element here. Therefore, the electrons are pulled closer to the bromine atom. So what did you learn? We talked about asymmetrical distribution of charge in a molecule, common shapes of polar molecules, including linear, bent, pyramidal, and tetrahedral examples. Need more help? Feel free to contact me. Have a great